So in the previous video, we discussed this idea of the work done by a spring. And using Hooke's law, we were able to show that the work done by the spring is given by this expression, okay, where K here is the spring constant. And the work done then simply depends on the final position and the initial position of the block attached to our spring. Okay, and so let's see an example of how we do that. Here's the example. So we have a spring block system. So this means that we have a block attached to the spring. The equilibrium position is at x equals 0. It's just a shorthand for that. So we apply a force of magnitude 80 newtons to hold the block stationary at x equals -2. So this is not the equilibrium position. We've moved it away from equilibrium, but we're now applying a force which balances the spring force, and that holds it stationary at this position. From that position, we slowly move the block so that our force does 4 joules of work on the system. The block is then again stationary. What is the block's final position? Okay, so let's draw a diagram first of all, just to make sure that we understand the problem. So here's our spring. Let's draw it like this. Okay, and attached to the end of that spring, we have our block. And the block currently at the start of the problem sits at this position, -2 centimeters. Okay, so here's the equilibrium position at 0. This is our x-axis. So we are applying a force to this block to hold it stationary. Now remember, because the spring is compressed, it always wants to return to the equilibrium position. So the force due to the spring is acting towards the center, towards the equilibrium position. So we are applying our external force in the opposite direction, and these two forces must be in balance in order to keep the keep the block stationary at this position. So we must have that Fs is equal to minus Fx, or external force, in order for these things to be balanced. Or another way of saying that is that Fs plus Fx is equal to 0. So the total force acting on our system is 0, therefore the acceleration is 0, the block remains at rest. So that's the situation initially. So let's actually write that out in words. Initially, the applied force Fx should balance the force of the spring. So what we wrote down previously, Fx plus Fs equal to 0. But remember that Fs is equal to minus Kx. That's the definition. So just to scroll back a bit here, F of x is just equal to minus Kx. That's the force due to the spring. So the force due to the spring, this thing is equal to minus Kx. And we know what the external force is. We're told what it is. It's 80 newtons. Okay, so we can now substitute those things in. Because the thing we don't actually know here is K, right? We know what X is, it's -2. We know what this external force is, we don't know what K is. Okay, so we're going to have 80 minus Kx equal to 0. So K is equal to 80 divided by X. And our X here is our 2 centimeters. So just make sure that we get the right units. This is 0.02 meters. And this gives us spring constant K of 4 times 10 to the 3 newtons per meter. Okay, so we've now determined what our spring constant K is. And that's important because if we look at the expression for the work that we derived earlier on, it contains this spring constant K. All right, so we know that. Now, the question tells us that we move the block slowly so that our force does 4 joules of work on the system. Now, when it says move slowly, what that means is that these forces will always be in balance, okay? We're not going to do any sudden movements where we have acceleration. If we're moving it slowly, then the forces are always going to be balanced, okay? So let's just write that down in words. So to move the block slowly and leave it stationary, the forces should always balance. Okay, so what that means is that just write down again what we had before, that our external force must be equal to minus the spring force. Now, remember our definition of work. Our definition of work was that it is the product of the force times the displacement. So the displacement is the same for both of these. Both of these forces are acting on the same block. The block is displaced by the same amount. So if the forces are equal, then what that means is that the work must also be equal and opposite. Okay? So the force is in balance, the displacement being the same, by necessity, and the work must always be balanced. Now, the good thing is we know what the work done by the spring is. We derived that in the previous video. So this is the work done by the spring. We just need the final and initial position. Of course, what we're actually trying to determine is the final position. We know what the initial position is. It's minus 2 centimeters. So given what we know, we should be able to determine the final position. So the work in balance like this, but we know that the work done by the spring is equal to minus a half k times xf squared minus xi squared. So the difference between these two positions squared. So that means that our external force must be equal to minus ws, as we wrote here. And so the minus signs cancel out here. So this is equal to a half k xf squared minus xi squared. We know what xi is. This is just equal to 0.02 meters. Okay, that's our xi. This is the thing we're trying to find, our xf. We know what this is. We calculated it in the first part of the question to be 4 times 10 to the 3 newtons per meter. And we know what the work done by the external force is. We're told in the question we do 4 joules of work. Okay, so what this comes down to is just rearranging this equation to find what xf is, and I'll leave that as an exercise for you to do. But all of this comes out to give us that xf is equal to plus or minus 0.049 meters, or that's equivalent to plus or minus 4.9 centimeters. So you can do the rearrangement to get that just by plugging these numbers in, but just to think about what that means, we started off in this equilibrium position. Sorry, it's not the equilibrium position, it's we're holding the block stationary at minus 2. Here's our equilibrium position at 0. And what this answer is telling us is that there are 2 possible ways that we can do 4 joules of work on the system and still end up with the correct kind of the work kind of balancing out as we had it. So either the block moves to this position, okay, so down here at minus 4.9, or it moves to this position at plus 4.9. In either case, our force does 4 joules of work, and we end up with the correct conditions. So either of these solutions is valid. It's just that in one case, the spring kind of helps us a little bit as we're moving along here, and then we're working against the spring as we go here. So again, this kind of balances out in terms of the work done. In this case, the spring is always working against us. So although we're moving a shorter overall distance from our starting position, the work done will kind of add up to the same amount in either case. Okay, so that's just the physical interpretation of this, but it all comes down just to the symmetry of the mathematics, that we have 2 possible values for the final position based on the fact that the work done is proportional to the position squared.